Welcome to the College of Optical and Sciences Colloquium series. Today is a special day, I guess, because I have two of my advisors in the room. So it is my honor to introduce Professor Frank Weiss from Cornell University to give the colloquium today. So I think I should take this opportunity to thank Frank for creating and maintaining such a good research environment at Cornell that young students and postdocs like myself can come and learn great science. And
it was our pleasure to have you.
So I spent 2 years in Frank's group, and it was really good time. I met a lot of good great students, and a lot of good researchers there, and I learned a great deal. Okay, so thank you for what you have done for me personally. So Professor Weiss received his bachelor degree in engineering physics from Princeton University, and then he went to UC Berkeley to get a master degree. And I guess you didn't like the California, the boiling weather there, so he decided to go back to the East Coast, where the weather is more exciting. And then he's got his PhD from Cornell University in 1989, and he has been on the faculty at Cornell Department of Applied Physics since then. So Professor Weiss' group, research interest has been in nonlinear optical impulse propagation and quantum dots, nanostructure, semiconductor nanostructure type. So please join me to welcome Professor Weiss. Thank you.
Well, good afternoon, everybody. It's a real pleasure to be here. I haven't been at U of A at the Optical Sciences, well, I should call it the College of Optical Engineering now, for at least 15 years. It's great there's so many great people here doing great work, and it's it's really been way too long. In fact, I was reminded earlier that I'm teaching nonlinear optics, and as I prepare the lectures, when I check a derivation, I always open up this old textbook by Newell and Maloney to check that things are right. So what I have in mind today is to first do a very tutorial. Whoops, I'm not getting the laser right. Do you have a laser by chance, Con? You must. What happened to it?
Experimental sort of non-functioning laser.
I teed that one up for you, didn't I? It worked when we did the test a moment ago. So, okay. Professor Maloney wins the argument. Okay. That'd be great. Yeah, thank you. I want to give a very tutorial introduction to multidimensional solitons. A number of you are students from different backgrounds, so those of you who are the experts, take a nap for 10 minutes or something like that. And then I want to tell you about work that this is not work that's finished. This is a progress report, and in fact, this is really our first results out of a new direction for us. And if anything, what I want to convey to you is that it looks like we stepped into a pretty fertile area, which you might not otherwise guess because it doesn't look very exciting on the face of it, but it looks like it has a lot of potential and a lot to figure out. And that's studies of pulse propagation in multimode fiber, and in particular today I'll only talk about graded index fiber. I'll talk about observation, or observation, documentation of the formation of solitons in multimode fiber and their fission. That's kind of the fundamental science, and I'll try to motivate why that's important. And an important overall thing, why do I say spatiotemporal? These are multiple modes with different temporal characteristics, so these are inherently spatiotemporal phenomena. Okay? And then recently we've done experiments to generate what you might call supercontinuum in multimode fibers. And this gives us we try to understand it, and then it turns out it might be a very useful source. And the way we do it is not by understanding it completely, but by shining light in one end, changing the launch condition, and looking at what comes out the other end. And by doing that, we can actually generate a lot of different light fields on demand by what looks like it could be a useful source. But that's secondary. So that's what I have in mind. And if you have questions, I don't mind at all if you interrupt. I don't know if that's against the rules in this seminar, but please, as far as I'm concerned. Okay, so Will Renninger got us started. He was a fantastic graduate student. He's now a postdoc at Yale. Logan Wright's been carrying the ball on this. And we collaborate with Dimitri Christodoulides, who some of you know from Creole, who's helping us with the more advanced aspects of nonlinear wave propagation, using code developed at Arizona, though. So, okay, to remind everybody, if we make a short pulse of light, you need a lot of colors. So if that propagates, because material has dispersion, different colors go at different speeds. So as the wave propagates, it spreads out. And your colors are sure funny compared to mine on my computer. But this is supposed to go from blue to red. Not sure why it's not. At least it's going in the right order of the spectrum in general, but it's... So the important point is a pulse spreads out and it picks up a frequency sweep or chirp. Okay? In this case, well, actually, let me say more. And the reason is very simple. Okay? It tends to be more useful to not think about the frequency sweep, but to think about the phase picked up. And remember, the frequency is just the derivative phase with a negative sign, because we take the time as e to the wave as e to the negative I omega t. Okay? So if I imagine working in a reference frame moving at the group velocity of the pulse, here's what a pulse looks like in the time domain. The leading edge is blue shifted. The trailing edge is red shifted if the dispersion is anomalous. So that's the intuition. We say for anomalous dispersion, blue leads red. Okay? But again, the better way to think, or I think a more helpful way to think about it is in terms of a phase that goes roughly like that. On the other hand, just turn it around for normal dispersion. And for silica fiber, that's for wavelengths below about 1,300 nanometers. Then the intuition is red leads blue. Okay? Now, the other effect that's very fundamental that we have to talk about is nonlinear refraction. This is the real part of the cubic nonlinear susceptibility, so intensity dependent. You can show within perturbation theory that the index of refraction is the constant we all learn about as kids, plus an intensity-dependent term. N2 is called the nonlinear index of refraction. And it's a very small number for most materials when they're transparent, but it can have big impact on wave propagation. So here's the simplest effect and an easy way to understand this. If the nonlinearity is instantaneous, and it's a good approximation that the nonlinearity arising from the electron cloud is instantaneous, okay, even on the scale of the cycles of the field, then we can just apply this equation point by point as a pulse has its intensity evolve with time. So if the intensity versus time looks like this, the index looks like this. Now, what I really should have is a tiny little pulse sitting on a huge background from that guy. Okay? But then the phase is just a copy, just follows the index, right? And then the frequency is the derivative of the phase, again with a minus sign. So you see that if you have just a nonlinear index, just nonlinear propagation, then a pulse picks up another, it's also a frequency swept pulse, but it's not a monotonic frequency sweep. It goes down and then up. Similar, by the way, N2 is almost always positive in transparent media. It's not always positive, but in transparent media it usually is. And we see here this is a derivative shape, so it swings down, then almost linear, then swings back down. Okay? And this is the process of self-phase modulation. And it's by itself, it's a way to make a spectrum get broader and broader and broader. Okay. Some people go running at the sight of nonlinear differential equations. One of my goals is to help students who are maybe not so familiar to at least be comfortable with these and look at them. Some of you are smirking and already looking like you're unhappy. I'm not sure. That we can look at these and actually get some intuition from them. This is the simplest nonlinear Schrodinger equation. It's called that because it has the same form as the Schrodinger equation of quantum mechanics, except that in place of the potential, we have something that's nonlinear here. Okay? So the way to look at this is to say propagation depends on two effects. This is group velocity dispersion. Beta 2 is the dispersion coefficient. It has a second derivative in time because it comes from a quadratic term in the expansion of the propagation constant in frequency. So it's really from a Fourier transform. And this is obviously a nonlinear term. So propagation is determined by dispersion and by nonlinearity. In general, if you take the dispersive spreading out of a pulse I showed you before and add on some nonlinearity, it only gets worse because the nonlinear part broadens the spectrum, so the effects of dispersion get even worse and a pulse decays. So either term in this equation will cause a pulse to decay in the sense of the energy spreads out in time, or the energy gets injected into other modes. But if we put them together in exactly the right combination, we can get a pulse that goes forever, and that's called a soliton. So a soliton is a solution of a wave equation that has two effects, either of which would make the pulse decay, but when you put them together, It stays forever. Okay, so obviously it's very interesting. Here's the dispersion in more detail. Here's the phase from dispersion if the dispersion is anomalous. The nonlinear phase always is just a copy of the pulse. So you can see how this guy can just fit perfectly in that guy. And so there's no time-dependent phase across the pulse, and so the pulse doesn't spread out. It spreads out just from the propagation. Okay? That works if we have the right magnitude, of course, because this has to fill in that, and the right shape. Okay? So this is the solution for a temporal soliton. And in fact, what we typically say is that the energy times the duration is proportional to the dispersion divided by the nonlinearity. That's the case for a soliton. And I may call this a nonlinear Schrodinger soliton. Okay? In fact, even more important, a soliton like this isn't just stable forever. You don't even have to launch it perfectly. If you launch something close to it, the field you launch will adjust itself by radiating till it gets to the soliton solution. So this is actually a nonlinear attractor. It pulls fields toward it, okay? Which is a very important point. There are only a few really important nonlinear attractors in fiber optics. So a soliton, instead of spreading out, does that. It's a telecom designer's dream, right? And of course, fascinating to us because anything that can go forever without spreading out is fantastic. Okay. This was red on my computer. So Professor Maloney, the Optical Sciences Center doesn't seem to have very good optics here, does it?
Actually, in every room on this building, I complained about it.
Okay, so we just showed you. By the way, this unfortunately humans love color, and I have quite a bit of color in my figures, so that actually it has information in it. So maybe I should be more concerned. I just showed you dispersive spreading of a pulse in time. Completely analogous, completely the same mathematically is spreading out of a beam in space owing to diffraction. So if we make a beam of light, now continuous, that will spread out because of diffraction. Okay? Well, we can use the same nonlinear index to counter that. Let's take a pulse that has, for example, a Gaussian beam. Imagine it propagating. That creates a bigger index in the center than on the edges, so material acts like a lens. This is called self-focusing, so this process can go like this. Now, in fact, if it starts to self-focus, unfortunately, the process keeps feeding on itself because the intensity gets higher, the effect gets bigger, the intensity gets higher, and that eventually goes to collapse. Collapse is collapse is an abstraction. We have to figure out what actually happens if it goes to that point. The answer is typically some other nonlinear effect occurs. Okay? Well, you can imagine we could have diffraction balance self-focusing just as dispersion balances nonlinear phase accumulation to make a soliton in space analogous to a soliton in time. Okay? So that would be something that propagates like this without ever spreading out. We do call that a spatial soliton or a self-trapped beam. And it's perfectly stable and a nonlinear attractor in one dimension. What do I mean by a one-dimensional beam? Imagine making an ellipse-shaped beam. So in one dimension, it's so big, diffraction is negligible, for example, or that direction is controlled by a waveguide. The other dimension is narrow. On the other hand, if you try to do this with a two-dimensional beam, like this beam, it never works. It's terribly unstable. It either diffracts or it goes to collapse. Okay? So there are no, well, I shouldn't say no. Through the mechanisms I've told you about, there are no stable spatial solitons, okay? Except in 1D.
So we turn on the second projector. It's the same color, so it must be the cable somewhere. So maybe it's.
Oh, that's an interesting. Yeah, you're right. Cable does sometimes do that.
It's not fully blocking.
There you go. Thank you. Thank you. Pilot error on my part. Perfect. Yeah, you can turn this one off. That's great. Glad I complained anyway. Okay. Now, imagine putting these two together. Okay? If we make a soliton in space and in time, imagine this, instead of spreading out in time and space, it goes together. That's called a spatiotemporal soliton. Or, not the very first person, but someone who thought about this, Jeroen Silberberg, called this a light bullet. Okay? Not a scientific phrase. And again, this is even more unstable. As you go to higher dimensions, these are extremely unstable. Okay? So this is an important point. Again, this is a tutorial, nearing the end of the tutorial. This is actually a figure of what was the first spatiotemporal solitons. This was actually ancient history. It was done 15 years ago in my lab. It consisted of an infrared beam at 800 nanometers and a second harmonic at 400, coupled to each other. And you see, by the way, it's only one-dimensional in space. Only this dimension was what we were interested in. And as that propagated, it broke into these filaments. Okay? So this is an example of this is just a modulation instability. Those filaments are actually about as close as anybody has come to making space-time solitons. If we could have stabilized them, they would have been space-time solitons. We couldn't. And in fact, the experimental setup precluded it. So instabilities occur, and if there are stable products of instabilities, those are very important. And that's one of the reasons we're interested in solitons, not just because they can propagate forever. If a wave is unstable and it breaks into something that is then stable, those things are like the modes of the system. They're the building blocks of the system. In 1D, solitons are the stable objects. Modulation instability will break a long temporal pulse or a wide beam into little things that are actually the solitons. Okay? So if they exist, solitons are important because they're stable objects, obviously, but also because they're the building blocks. The solitons to nonlinear systems are like eigenmodes to linear systems, atoms to materials, prime numbers to numbers, whatever analogy you want to use. Okay? And a huge amount of our understanding of phenomena in 1D builds on the idea of solitons. Mode-lock lasers, supercontinuum generation, rogue waves, which are popular now. These are all viewed as interactions of solitons at some level. Okay? Again, in 3D, true solitons are completely unstable. Okay? There are other interesting, very important waves that are not solitons, and doesn't mean they're more or less important. In fact, people sometimes now use the word light bullets to refer to conical waves, X waves and O waves. These are waves that emerge from instability, for example, in filamentation. This is a picture from the University of Michigan where this student broke every safety rule in the book over Christmas break in 1995 by shining a high-power laser down the hallway. And lo and behold, they found that it didn't spread out as much as they expected to from diffraction. So they realized they were onto something, and this is now a very active area of research, including here at University of Arizona. And people now, of course, this is interesting. You can shoot it 10 kilometers into the sky. It's white because of cell phase modulation to some degree, and so you can use it to do spectroscopy of things in the sky 10 kilometers away. And there's even a truck with a high-power laser that drives around the countryside of France and Germany that does this. Okay, people get paid to do this, right? So, okay. So what does all this have to do with optical fiber? This is a talk about fiber. Okay, I want you to start thinking about multimode fiber as something that can support spatiotemporal evolutions. Questions? Am I allowed to ask for questions? No? Yes?
I think I might have misheard you, but at the beginning, were you saying that the temporal section of the nonlinear is unstable or stable?
If it's just 1D? No, surely you can make a 1D temporal soliton, absolutely.
Okay, but it's unstable in 3D.
Absolutely. Nobody has made a three-dimensional space-time soliton in a homogeneous medium. It's one of the major unsolved problems in the field of nonlinear waves, I guess. Okay, here's how I want you to think about it. Imagine we start in 1D. Here's linear propagation of something spreading out in time. With nonlinearity, we can make this localized. Okay? Now imagine just reducing the strength of the waveguide slowly but consistently. Okay? Then what happens? Well, the beam spreads out like this. If it's going to be localized like this, it is going to take more nonlinear effect to make this be localized than it took this to be localized. Okay? We have the other two dimensions to take care of, in a sense. That's the intuition I want to get across. But also, I want you to see that as we make a waveguide bigger, I think many of you know that this will support more and more transverse modes. So that's a way to go from a strictly one-dimensional system to free space, increasing the number of modes as you go. So a multimode waveguides are a way to make the transition between 1D and 3D. Okay? And from the point of view of if our goal is to make space-time solitons, which it isn't necessarily, this would be a way to study an intermediate case where we might have a chance to succeed. Because in 3D free space, it's very difficult. Okay. So multimode fiber. It's been used in local area networks for 40 years or something like that. Very, very common. It's now gotten a resurgence of interest after people lost interest in it because people are thinking about telecom. You know, in telecom, people fill all the time slices with information. Then people put different colors down the cable. So that's called wavelength division multiplexing. But we always want more bandwidth, right? I hear this amazing statistic. Netflix accounts for 10% of the overnight internet traffic in the US. Think how many, I mean, that's an astonishing number. How many terabytes is that, right? So how are they doing it? This is mostly coming over the fiber as people watch movies at night, right? So what's the degree of freedom that's left? Well, people are saying, let's make the fibers bigger, have multiple modes, and have individual channels in multiple modes. So telecom is now studying mode division multiplexing or space division multiplexing. Of course, there's also interest in making fiber lasers more and more powerful or transmitting more and more light. This is almost always limited by excessive nonlinear phase accumulation. So the bigger you can make the core, the better you can do without distorting a pulse. So this is a tutorial, one slide on graded index fiber. The index profile, I think almost all of you know this. I'll go through it quickly. The index profile is almost parabolic. And in this case, the important thing for us is that the different modes have propagation constants that aren't as different, they don't vary as dramatically as the propagation constants in a standard multimode fiber, a step index multimode fiber. Okay? Here's what some of those modes look like. They come from solutions like this or associated Laguerre functions. And some examples of the modes. And I'm showing these 5. These are the lowest 5 cylindrically symmetric modes. And I'm showing these because these are the most pertinent to the experiments I'm going to show you about. And we use these in a lot of the calculations that I'll show you. Okay? Of course, the simple intuition about a graded index medium is that it acts like a lens at every point. So rays that go off, come back, go off, come back, et cetera. So this evolution in a graded index fiber is the first thing most people learn about. Okay, so now this is an equation that includes a single field equation for all of the effects that happen in a graded index fiber. Propagation is determined by several things. By the way, notice all have I in front of them, so they're all phase modulations. There's no loss in the system. Here's transverse diffraction. Here's dispersion that I told you about. Here's nonlinear phase accumulation. And here is the parabolic potential. So this is a harmonic potential just like a harmonic oscillator. Okay? So the wave is influenced by all of those things. And this happens to be the equation that's used to model Bose-Einstein condensates. So there's interest in other fields. A lot of study of the Gross-Pitievsky equation in that context. Okay, so what happens when we let an ultrashort pulse propagate in a graded index fiber? I'm not going to go through these. My point is to show you that a lot of smart people thought about this before we did. We're not the first ones. Okay? However, almost nobody did experiments. So people from the very beginning wondered, could we make, actually, I skipped, oh no, okay. So these are papers that built up you can imagine this is pretty complex. You either do this by a complicated single field model or you do it by coupled mode theory. We have a separate equation for every mode that's propagating, and I'll show you a little bit about that. So the machinery has been built up to do this largely from University of Southampton, but not completely. People thought about making solitons in multimode fiber almost from the beginning. In fact, Hasegawa was the person who predicted that solitons could be made in fiber. Soon after, he thought, okay, probably ought to happen in multimode also. His model wasn't very realistic, but he was at least thinking about it. Okay? And again, people have thought about this ever since. But there have been almost no experiments on this. Okay? And we tried to think about why as we got into this field. And the answer seems to be that as soon as single mode fiber became available, everybody started paying attention to single mode fiber. And this has been a fantastically productive area of research for the last 20 years or something like that, even more. And people didn't pay attention to multimode fiber except in the simple applications like local area networks where the details didn't matter. So it wasn't an area of research. Okay, so this is a solution of the Gross-Pitievsky equation that I showed you, numerical solution. And we should look starting from the right side. This is the width of the pulse of the beam. as a function of distance, 50 meters of fiber. See, it oscillates a little bit. We launch something like this, and then it gets very stable. Okay, so that's something we would think of as a soliton. Sorry, this is the temporal duration. My mistake. Here's the width as a function of distance, and what you see there is actually just the grin making it go like that, the graded index. Here are the temporal and spatial profiles of the pulse, and this is the spatiotemporal profile. So this says numerically soliton solutions exist. So here's a simple experiment. Launch a pulse of light. What these numbers mean is just that let's say we look at propagation through 100 meters of fiber. We let it go first through a single mode fiber because then we control what we launch. We launch a nice, perfect lowest order mode into the fiber. And we arrange that the pulse is short enough so that the length over which it increases by dispersion is very short compared to the very short compared to the fiber length. In other words, if we launch this at low power, it will spread out very quickly. But we have strong nonlinear effects. And we measure what comes out on the other end. So first thing we did is, I'll call this baby steps. We started with just the 3 lowest order cylindrically symmetric modes, which we could launch reasonably well by the technique I showed you here, just having it come out of a single mode fiber. Okay? So here's the way to think about it. If we launch those 3 modes together at the beginning of the fiber, they spread out for 2 reasons. Number 1, each mode spreads from dispersion. Second, the different modes have different propagation constants, so they have different velocities, and so the modes spread out from each other. So this is what would happen in linear propagation. Okay? In fact, when we do the experiment, we can't even measure anything at the other end. It's spread out too much. Now, here's an experiment on soliton formation. We increase the pulse energy only to half a nanojoule. And this is a little confusing. The red is the input. So the red is the input pulse in time, and the red here is the input spectrum. We launch that through 100 meters of fiber. And this is the input field. What comes out the other end, you see, is almost the same duration. And this is 100 characteristic dispersion length. So in linear propagation, this spreads out by a factor of 100. And you see the spectrum picks up some structure, which is very typical for a soliton. And the mode that comes out is actually somewhat larger. Okay? Now we have the 3. This is comprised of the 3 lowest order cylindrically symmetric modes. So this is a step. This is an observation of a temporal soliton in a graded index fiber. That's why I call it baby steps. Here's what the spectra look like. That's the spectrum of the soliton. And if we turn up the energy, remember the soliton obeys the energy times the time is just the dispersion divided by the nonlinearity with some constants. So that's theoretical. So it should have a shape like this, and indeed we see this. And in fact, the size agrees well with the mode that we measure. But another thing happens, and this is very common with anomalous dispersion. When you launch a pulse, you see what happens. The spectrum shifts further and further to the red. This is from stimulated Raman scattering. Okay? It's very strong. And this happens in single mode fiber. And in fact, we can model this with a theory from single mode fiber. What's called the soliton self-frequency shift is modeled theoretically by this expression for the change in wavelength. Depends on the dispersion, the effective Raman response, the pulse duration. And you see the strong dependence on the pulse duration. And this actually fits theoretically too. Okay? So this is all pretty good. But on the other hand, well, let's talk about what it means intuitively. This is the linear propagation. This is the nonlinear propagation. So we made something that doesn't spread out. But to be honest with you, it's not that exciting because it still has the grin really taking care of the lateral dimensions. Okay? So the spatial evolution, we don't see much of a nonlinear effect. And in a way, it just acts like a big single mode soliton. So in a sense, kind of boring. But as I said, it was a baby step. So let's go on. I'll show you simulations now. It helps to look at a mode resolved picture of what happens. Here are the lowest 5 cylindrically symmetric modes. Here are a handful of other modes that we mix into the simulation to involve something that's not cylindrically symmetric. And we've done numerical calculations with mixtures of these. And the main results actually don't change much. OK, so let me explain these to you. There's a different way of viewing what I showed you before. Here are the 5 modes launched into the fiber as a function of time. Here's the propagation direction. you see what happens. They spread out in time individually from dispersion. They spread out from each other because of the different modal velocities. Oh, I got it. Okay. And of course, it's linear propagation, so the spectrum doesn't change for any mode. Okay, what happens in soliton formation? We turn up the power a little bit. We launch something, and you see here are 3 modes that's synchronized. Dispersion, they don't spread because of dispersion, and they're stuck together by the nonlinear coupling. Okay? And how does this happen? Well, one contribution to it is the spectrum actually shifts a little to shift the velocities so that these guys can line up. Okay? Obviously nonlinear. Okay, so one thing you might think about is what on earth should we actually measure in this experiment? Think about it. What's coming out the end of the fiber, everything varies. Time, space, and wavelength. So in principle, we need a spatio-spectral temporal diagnostic, and we're going to need it to cover hundreds of nanometers range, as you'll see. Okay? That's hard. So here's what we did. We decided that we should record the overall average spectrum. So we arrange a spectrometer to basically defocus and give us the integral of the spectrum because we want to compare to calculated power spectra. We image the near field, we image the end of the fiber onto a camera. So we're basically taking a picture of the near field. And then for comparison, we measure the pulse by measuring an autocorrelation, and we do it for the whole field. So when we compare to theory, we compute the whole, we integrate over the space dimensions. Okay? And then what we can do to change the launch conditions, therefore the modes that we excite initially, we can move this. I mean, think about this experiment. We have a laser that's pretty modest. We have a lens on a 3-axis translation stage, and we have $10 worth of fiber. Okay, so first thing, we really wanted to see multimode solitons, and here's the idea. I'm not going to go into this in too much detail. For a soliton, and by the way, an important point to make, solitons are actually families. We can change the energy as long as we change the duration also. Okay? So here's the expression for the soliton, the product of the energy times the duration, dispersion over nonlinearity. There's the size. And our argument is, as I said at the beginning, if we're going to make a multimode soliton, we're going to have greater nonlinear phase shift, therefore greater energy, to overcome the mismatch of velocities between the modes. We're going to have stronger coupling. So this is a plot of a bunch of experiments where we did the experiment I told you before and measured what came out. Those are in red. And a bunch of simulations, points are in blue. And what we're plotting here is the slope of that energy versus 1 over pulse duration, because that's proportional to the nonlinear phase. So this axis is a way of expressing the amount of nonlinear phase that's required to make the soliton. And this is as a function of the size of the beam that we launch. If it were a single mode soliton, it would be the black line. And so we see pretty good agreement, and in the end we conclude, and we can infer how many modes there are. There are about 10. So these are indeed multimode solitons. Why is that significant? Because think about 10 different fields interacting, all coupled, all nonlinear, so there's a lot of diversity already. It's actually complicated. Okay, so now let's keep going. Okay, so that's actually a first important kind of summary point. That's the way to understand multimode solitons. Questions? Can I give a quiz question? Sure. Everybody still awake? Okay, now let's keep going. Perfect nonlinear Schrodinger solitons, the solutions to the equation I showed, are perfectly stable. In general, there will be other terms in the equation in any realistic situation, and those make them unstable. And one of the ways they become unstable is by breaking up. So they undergo fission. Okay? So here's what happens if we go to even higher energy than we did to make the solitons. We launch something. They form a soliton. Here's a bunch of modes locked together. But then that fissions. What happens is the soliton starts to compress in time. The intensity gets very high. Then that process is arrested or stopped by fission occurring. The same thing that happens in a 1D temporal soliton. And as a result, the question is, what are the products of that fission? Well, there might be other temporal solitons, or in this case, here's a temporal soliton, a bunch of modes locked together, a multimode soliton. But now it's a long way away. This one is a Raman soliton with many modes. Okay?
Why are you using the gradient index fiber? Because the modes are closer together?
Yes, good question. And we will study step index multimode fibers. All of this could happen, but probably at much higher power, maybe in practically higher power, in step index multimode. GRIN, by the way, the answer is yes. The propagation constants are closer, so they don't go away from each other as fast. There's not as much to overcome. But it's also a downside, because remember, now you always ask, well, isn't the linear doing a large part of the work? Right? It's not as interesting for us to isolate the nonlinear part. So it's both, but we can see interesting things. Other questions? By the way, I see people taking notes. You can keep the slides. I'll leave a copy of the slides, and you can keep them so you don't have to. Okay, so here's a close-up on it. So this is an example of the result of the fission of a multimode soliton into other multimode solitons, and in this case, a multimode Raman soliton. Okay, so how do we understand this? And I'm going to have to think. I don't want to overwhelm you with information. Remember, so these are measurements. Here's an example of simulations where we calculate the autocorrelation function of the whole field. That's how we measure short pulses. This is just a zoom in of these. And what you see is we have a big peak at 0, and then we typically have some small peaks. By the way, remember, we're launching 500 femtosecond pulses. You see these are compressing all the way to well below 100 femtoseconds. Okay? So it's a very strong effect. This is experiment for comparison. And the way to understand this is the smaller peaks in the autocorrelation come from less localized modes. They're ones that are spread out. By the way, how do we know all this? Because the experiment and the theory, and I'm going to show you more data, agree pretty well with each other, we interpret it in light of the simulation where we can see everything. Okay? So these small ones are from the bigger modes. The big one is from a lower order mode. And that's the one that's going to get Raman shifted. So in a sense, the Raman process is very, very important here. In a sense, it focuses energy into the lowest order mode. And the way to understand that is, as light shifts to the red, the part that's still at the blue can give Raman gain to the red part. Here's what happens in space. Here's an example of a field we launched. Obviously, this is many modes. And as we turn up the power, we see this evolves to a single pulse and eventually to something like that. Here's a simulation of the spectrum under the same conditions. Here's the spectrum that we measure. See, the agreement's good. And an important point is, if we look at the whole spectrum, this is the beam we measure at the output. If we put a filter here, so we isolate the Raman soliton part, we just get this tiny little part. So Raman is making energy go to smaller and smaller part of the mode. And this is about the size of the fundamental mode of the GRIN fiber. Okay. So now to keep going to higher power. Regime 1 was linear propagation. Regime 2, soliton formation. Regime 3, soliton fission. Now to the last regime. If we launch a pulse at high energy, by the way, the energies that in the past, I should have been more explicit, were about 15 nanojoules to see fission. Still very modest. If we launch 100 nanojoules to a microjoule, here's the spectrum as a function of distance in propagation. And you see what happens is it blows up and spreads out. And those of you who are familiar with short pulse propagation will look at this and say that's continuum generation. Okay? And in some ways, it does look like a continuum. It also has some features that you never see in continua from single mode fibers. Okay? And here's what it looks like in time. And by the way, this is a simulation, and we'll show you experiments done in only 1 meter of fiber propagation. Okay? Okay. The first thing we notice is spatiotemporal dynamics. And this accompanies the Raman. So here's a launched pulse at a few nanojoules going up to almost 200 nanojoules. You can see the Raman soliton splitting off here. Here are the beam profiles as we increase the pulse energy. Now, by the way, all of these are below the critical power for self-focusing. The critical power is defined as when the tendency to focus just overcomes the tendency for diffraction. So ordinarily, in homogeneous media, if the wave exceeds the critical power, it goes to collapse, roughly speaking. Here, the critical power is 10 megawatts. The actual power that we launch is about 1 megawatt. So it's way below the critical power for self-focusing. We wouldn't expect any self-focusing. But we see things that sure look like whole beam and small-scale self-focusing. We see filaments and filaments, and 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 we see filaments and filam speckles, things like that. Okay. Well, the Raman shifting makes a multimode soliton, and that shifts out of range. Our camera is in gas. It can only go to about 1800 nanometers or 1750. I don't remember. So what we're seeing here, the soliton actually goes. What's left behind are what are called dispersive waves. Dispersive waves are just ordinary waves that disperse. When a soliton undergoes, solitons can interact with dispersive waves. And solitons in higher order modes are left behind. So that's what's responsible for all this structure. So this is a kind of self-focusing, but it's not the ordinary self-focusing we talk about in Kerr media. Okay. And now this is to show you that we can determine the continuum experimentally by how we launch the beam. And this, we don't know why it's coming out the way it is. We just look at the output and vary the input. It's like aligning a laser. You don't know what you're doing, but you know what its consequence is. So this is a continuum for, this is the infrared section. Remember, we're launching 1550. So here's a range of wavelengths we see. Here's what we see in the visible. And we can identify a lot of these things, and they look analogous to what we see in single mode fiber. This is the Raman soliton. This is a dispersive wave from the pump, which is here. This is a series of peaks I'll tell you about. This is third harmonic generation. This is a dispersive wave from the Raman soliton. And you figure all these out by looking at the dispersion relations. Okay? Remember how complicated this is. For every mode, we have a different dispersion relation. So we have to look at where things overlap. So here's, and this is 20 dB variation. So if we turn up more, if we want just more power, we can get this. We see the beam changes a little bit. Let's say we want to make this continuum more smooth, which people want for some applications. We move the beam around a little bit. We can make it smooth. Here's what the beam, how the beam comes out. If we want to maximize the dispersive wave, then we can adjust till we get that to happen. And if we want to maximize the Raman soliton, that's this guy over here, we can adjust for that and take away the energy here. So, I mean, I want you to understand, we're looking at over 1,000 nanometers of bandwidth, over an octave of bandwidth here. And we're rearranging stuff in the spectrum according to how we launch the pulse at the input of 1 meter of fiber. Okay. Question? Yes?
When you say how you launch it, what do you mean? Like, do you change the pulse input?
Literally changing the position and the angle of the beam going in. That's all it is. Okay? Keep the pulse the same. So this could actually be very useful. Here's what that spectrum looks like. Here's the pump. Here's the Raman soliton, about 2,200 nanometers. That's actually a very energetic ultra-short pulse. In fact, that competes with almost anything anybody's generated at 2 micron wavelength, which is a very interesting region. In fact, and those of you who know about short pulses will look at this and say it's frequency distorted, it's chirped because it has the secondary maxima of the envelope down here. We can't avoid that in the measurement. So to make it practical, if we want to, we'd have to do something about that. Let's go over to the visible side. So here's the spectrum that we get just as a reference point. If we want to maximize the dispersive wave from the Raman soliton, and by the way, you don't really need to know what these are. Those are the details of the understanding. You just need to appreciate that we have a way to engineer what comes out of the fiber. Okay? Well, we can adjust till we get that. If we want to maximize a series of peaks, which is a frequency comb actually, we can adjust till we get a frequency comb here. If we want to minimize the peaks, we can do that also. Put the energy here. By the way, the overall integrated energy isn't changing much. It isn't changing at all. We can maximize the dispersive wave from the Raman soliton, or we can make another frequency comb. And if you're wondering if there's much energy in this, this is what it looks like live in the lab. Remember, that's coming from launching 1550 nanometer light into a $10 fiber. Okay? So the important point here is, as the question acknowledged, how are we doing this? Just by adjusting the launch. We need a cool name like launch engineering or something. I don't know. It's really simple. And if we want to maximize boring old third harmonic generation, we can basically get all the energy to go into third harmonic. Okay. So what do we see? It's not really the point of this, but this is probably the broadest continuum anybody's ever made in silica. It almost covers the whole transparency range. Humans love rainbows, right? Optical scientists love rainbows, okay? So we know people have been making supercontinua for 40 years, and we still love them. We don't get tired of them, okay? So this is remarkable, and there can be reasons that's important. Let me not downplay that. A lot of the features I've interpreted in terms of words we use for continua from single mode fiber. Some of those are correct, but there are more complicated things. Some of the features, like the peaks I showed you, never show up with single mode fiber. Don't forget, the processes here are all spatiotemporal. Obviously, that doesn't happen in single mode fiber. What are these combs? We don't know. We've racked our brain. We've run millions of simulations. Not millions. You can't do millions of 3D simulations. We've run hundreds of simulations. It seems to us that this must be part of it. If you think about a soliton propagating in a fiber, that's an intense pulse. It changes the index of refraction locally in the material. A dispersive wave has a different velocity from a soliton. So a dispersive wave actually is faster. And sometimes they're called Cherenkov radiation, optical Cherenkov for this reason. It can catch up to the soliton. Well, if it encounters that index in homogeneity, it can bounce off, right? It can kind of reflect. The soliton, therefore, acts like a cavity, okay? And so that's one of the things we think may be at work here. And this is actually related to the idea people have that a pulse propagating in an optical fiber can make the analog of an event horizon. Okay, it can make like a black hole or a white hole. So this is potentially interesting. Mostly sounds science fiction to me. But it looks like this is actually relevant here. But there are some things we don't understand for sure. Okay, so let me summarize. We've studied soliton formation in multimode fiber. Again, amazingly, nobody had done this. I mean, Grin fibers existed for 40 years, and nobody had launched pulses in and looked for this. I've given you just a little bit of feeling. There's no time in a talk like this to lay it all out systematically, but I hope you understand that these are spatiotemporal in nature. We see space-time dynamics. We see the soliton formation. We see evidence of the fission. For applications, this is relevant to time division, to mode division or space division multiplexing in telecom. It's probably bad, I guess. But put it this way, if people are going to put information to different modes of a fiber, they need to know about this, obviously. And eventually, you want to put as much power in as you can and not have the signal get distorted. And of course, this will be relevant to high-power lasers, amplifiers, transmission applications. If we have a fiber laser, and that's actually pretty modest, microjoule of energy and 500 femtosecond duration, not hard to achieve at all, and then a piece of Grin fiber, you can almost, it's a bit of an overstatement, but you can almost make temporally, spectrally, and spatially tunable pulses on demand. Again, we don't know how, we adjust the input. So simple way to make the 2100 nanometer pulse I showed you is a megawatt peak power. Okay, looking ahead, as we've done this, we've realized that obviously this is very complex, and that's hard to sift through. So we did the baby steps with 3 modes. We did the continuum I showed you, which is many modes and much nonlinear coupling. We've realized we'll probably be served well by going back and doing experiments in so-called few-mode fibers, where we can isolate some effects and really get systematic understanding. Again, there was a question. Going to step index is a natural thing to do. Probably have to take the power up a long way. It's sitting there to be done, though. It's an obvious good idea. Scientific things, we think it might be interesting to look at the effects of disorder. Everything I told you about was in passive fiber. Might be interesting to put in gain and loss. Okay? And that's a step toward making lasers and amplifiers. Nobody knows a good way to make a short pulse laser with multimode fiber, for example. Usually the presence of higher order transverse modes destabilizes mode locking. We'd have to learn how to control things in space and time to do it, but that's a big picture direction that could be interesting and fruitful. So we're thinking about it. At the moment, we actually see so many directions to go, we're not sure which to go yet. So we're at a natural point. Having gotten some results, I hope to have convinced you that it's a fertile direction with a lot of possibility. So thank you for your attention. We always thank our sponsors for their support. Happy to answer questions.